I should have been more careful. Reduction is you're gaining hydrogen and electron. Oxidation is the opposite. Oxidation is you're losing hydrogen, you're losing electron, but you're gaining oxygen. The oxygen part, delete that, you don't need to know. Again, we want to focus on hydrogen and electrons only. Another chemical reaction you need to know is phosphorylation. This one is easy. When you phosphorylate a molecule, you just basically add phosphate. It's not in your notebook, why are you not writing? So phosphorylation is you're adding phosphate to a molecule. Miss, what is phosphate? You're all in chemistry. Phosphate is PO4 minus. Okay, you're adding phosphate to a molecule. There's two types of attaching phosphate to a molecule, either substrate level or oxidative phosphorylation. Miss, what's the difference? This one is a direct addition of phosphate to a molecule. Direct addition. This one is indirect, meaning something will happen first before phosphate will be attached to your molecule. So direct attachment of your phosphate, indirect attachment of your phosphate. For both, it's addition of a phosphate to a molecule. And then the third, let me finish. Decarboxylation. Decarboxylation. Decarboxylation is when you say D, like remove, like take out, right? What are we taking out here in decarboxylation? Carbon. Let's just focus on carbon, for example. That will be in the form of carbon dioxide. So we're removing carbon, decarboxylation. So the 6 carbon becomes like smaller and smaller, 5, 4, 3, 2, 1. That's decarboxylation. All right. So this was your basic equation, right? Very simple. This whole process of respiration converts ADP and phosphate into ATP. Now, what are the different processes involved in production of your ATP? So we have these 5 processes: glycolysis, link reaction, Krebs cycle, electron transport chain, chemiosmosis. These two, please write in your notebook. This together makes up oxidative phosphorylation. So oxidative phosphorylation has 2 parts: electron transport chain and chemiosmosis. Okay. Now, before we look at each step, can you open your book? There's a purple box there for the diagram of your mitochondria. There, purple box. It says annotating diagram of a mitochondria. So you need to know how to label, identify the different parts of the mitochondria. Why do we have to learn the parts of the mitochondria? Because that's where the reaction, where the cellular respiration happens. Okay. Minus glycolysis. Glycolysis is in the cytoplasm. The rest of the processes happens in the mitochondria. So we need to know the structure of the mitochondria. So let's look at the different parts here. So the first, I want to start with the membranes. Remember in our previous unit, we said mitochondria together with chloroplast, they're double membrane. In other words, they have 2 membranes. We have the outer membrane, right? And then inner membrane. Sorry, I'm using my cursor because I'm recording this, right? So outer and inner membrane. Now the space between the outer and inner membrane, nothing fancy, you call it intermembrane space. So in between membrane space. So outer membrane, intermembrane space, inner membrane. And this inner membrane, they have enfoldings, like if it's folded. The folding is called a cristae. Okay. This folding of your inner membrane is called a cristae. Okay. Next, there would be fluid inside your inner membrane, this big part. Again, nothing fancy. We call it the matrix. Matrix means like a not basement, like a, what do I say? Matrix. That's where you put things. A matrix. Okay. And then let's see. 2 not so important things. Not really involved in cellular respiration, but nice to know. Mitochondria has its own ribosome. It's a smaller ribosome, 70S ribosome, and it also has its own DNA. Okay. Miss, are they part of cellular respiration? No. You just have to know that they also have their DNA. They also have their ribosome. Children, ladies, can you keep it low or like move somewhere? Because my brain wants to listen to you too. I'm slowing down. I'm trying to listen to you. All right. So this is a diagram, very simplified. You know the different parts, but you need to know how to label electron micrographs as well. Okay. So an electron micrograph, same thing. If it's pointing here, if you're unsure during the test, just ask me. So if it's pointing here, outer membrane. If it's pointing at this inner folds, that will be your inner membrane. If it's in between, intermembrane space. If it's pointing at a dot, it's a ribosome. Okay, here we go. So I'll emphasize again. Remember, there's 3 chemical reactions: oxidation, reduction, phosphorylation, and decarboxylation. All right, more clear definitions here of oxidation and reduction. So for reduction, I said we're gaining electrons and hydrogen. Ignore oxygen. So we're gaining electrons and hydrogen. So in your brain, don't switch it like I did. Reduction, but you're gaining. Okay, reduction, but you're gaining. In chemistry, we learned that reduction, you're gaining, but what you're gaining is something negative. So that's why reduction. And then oxidation will just be the opposite. Whatever you gain in reduction, you lose in oxidation. Okay. A good way to remember that is oil rig. Do you know what an oil rig is? You explore fossil fuels in the ocean. So you dig down the ocean floor for petrol. Okay, oil rig. This facility is called an oil rig. While oil rig, oxidation is loss. Rig, reduction is gain. Please try to simplify. I hope you understand what's happening here. So you have to know that there are electron carriers in the cell. They just basically pick up an electron, carry it, and put it somewhere. Those are electron carriers. So we have 2 electron carriers, NAD plus and FAD. So I'll just focus on NAD. Whatever happens in NAD plus is the same as FAD. So this electron carrier seems to be losing or gaining hydrogen here and electron. Gaining. Okay. Reduction or oxidation? Reduction. So NAD plus is reduced to become NADH plus H plus. Remember, NAD plus becomes NADH plus H plus, while FAD, when it's reduced, becomes FADH2. Remember that today, because I'll just keep repeating myself for photosynthesis. For photosynthesis, we also have electron carriers. All right. So if I say there are electron carriers, whenever they gain that electron to become this, at some point in the process, they can lose that electron also. Here, it's showing you how they're picking up electrons. Okay, later, they're going to drop off that electron somewhere else. All right, let's start with the first step of cellular respiration, which is glycolysis. The name is nothing fancy. Lysis means break, split. So what are we splitting here? Glucose. So as I call it, glycolysis. All right, let's look at the steps now. God help you. All right. So first of all, we start with glucose. Glucose. Look at what happened to glucose. It became glucose 6-phosphate. What chemical reaction is that? We're adding phosphate. Phosphorylation. So first, step 1, glucose is phosphorylated. Okay, so it's added a phosphate. So we just keep switching between the two. I like molecules too. We start with glucose. We're adding a phosphate. Where did the phosphate come from? Right there. ATP becoming ADP. So we're actually using ATP in the first step. Okay. Step 2, glucose phosphate became fructose 6-phosphate. That sounds like another phosphate. Look at this one. Fructose 1,6-biphosphate. What does that mean? You're adding how many phosphates? 2 phosphates. So if we added 2 phosphates, we used how many ATP? 2. So we use 2 ATP to phosphorylate glucose. Clear? Clear from here? We use ATP to phosphorylate glucose right there. You have 2 phosphates in your glucose now. Miss, do I have to know fructose 1,6-biphosphate? No. Maybe you just need to know there's 2 phosphates there. Or some books will use hexose biphosphate. It means hexose 6 carbon sugar with 2 phosphates. Hexose biphosphate. I don't know what the book uses. Did the book use hexose biphosphate or fructose 1,6-diphosphate? Fructose biphosphate or 1,6-biphosphate. Okay. You don't need to know like the actual names. What you need to know is glucose is phosphorylated. Now 2 phosphate. Next step. Very easy. This is how many carbons? 6. Split it into 2. 3. Split it into 2. It becomes G3P. Split it into 2. It becomes G3P. Okay. So lysis. First step is phosphorylation. Then here is lysis. Split it into 2. So if you split it into 2, you have something that looks like this, right? Split into 2. Next step. Actually, I like this. But anyway, for clarity, I'll just keep going back and forth here. Next step is, what's happening to NAD here? NAD plus. It's reduced. So NAD plus is reduced. Very good. What happens to G3P? G3P is oxidized. Where did the H and the electrons come from? G3P. Whenever something is oxidized, something is reduced. So you can say that G3P is oxidized, reducing NAD+. Or you can say NAD+ is reduced because G3P is oxidized. Okay, clear? Review again. Phosphorylation, right? Lysis, correct? Lysis, you're splitting it into 2. And then next is reduction of NAD+, or oxidation of G3P. Okay. That's just another fancy name for G3P. There's 2 different ways to name it. But it's fine for you to remember G3P. I'm fine with it. It means diceraldehyde-free phosphate, if I'm not mistaken. Okay, so after reduction here, look at what the name is here. 1,3-biphosphoglycerate. Mister, do I have to know that? No. But here's what you need to know. So you split it, right? After reduction of NAD+, what is this color? This phosphate. So we phosphorylate it again. We phosphorylate it here. We phosphorylate it here. Please listen carefully. Phosphate here came from ATP. Phosphate here came from free-floating phosphates, not ATP. These are free-floating phosphates. Normally in the book it uses the symbol PI. PI means free-floating phosphate. Okay, so we split it, and then we added phosphate again. Then from here to here, what's happening? From here to here, ATP formation. So this one, so we start here. It has phosphate, right? So we remove that phosphate. We add it, and then we remove that phosphate to form ATP. Let's look here again. So we added the phosphate, correct? After I added the phosphate is removed. Where does it go? To ADP, to form ATP. So in short, how many ATPs can you form from this molecule? 1, 2, 3, 4. Okay. So in glycolysis, we form 4 ATPs. And we used how many ATPs? Two. We used two. We formed four. So the net yield of ATP is 2. One glucose molecule yields 2 ATP in glycolysis. Okay, let's continue though. So ATP is formed here already. Remove that. We have 2 ATP here. The whole process from here down here, NAD is reduced. So if we go back here, please, like this one. Okay, so the overall products here, the overall products of glycolysis is, from glucose, your first product will be now pyruvate. This is pyruvate. How many pyruvates? 2 pyruvate molecules. And you also produce 2 ATP, net ATP. And then you also produce NADHs right here. So 2 NADH, 2 ATP, 2 pyruvate. That's easy to remember, right? If you don't remember the numbers, that's fine. You can just say you have pyruvate, you have ATP, you have NADH. Clear? Pyruvate, ATP, and NADH. That is glycolysis. This happens in the cytoplasm. This is not in the mitochondria yet. But you can bullet point the keywords here. So you can put first bullet point, cytoplasm, right? Cytoplasm. Second bullet point, glucose, phosphorylated ATP. First step, we add phosphate to our glucose, right? What did we use? ATP. So second bullet point, glucose, phosphorylated ATP. Next step, split. You can just say that, split. Glucose is split, right? Step 4, you can say oxidation. Oxidation, or how can you summarize it? Oxidation,
Removing hydrogen.
so triphosphate is oxidized. This one, triphosphate is oxidized while NAD plus is reduced. Triphosphate is oxidized. Can you put a plus here? Triphosphate is oxidized while NAD plus is reduced. Next, how many ATPs are formed? 4 ATPs are formed. Please add substrate level phosphorylation. 4 ATPs formed, substrate level phosphorylation. And then final product is 2 pyruvate. That's the summary of glycolysis. You want to draw this diagram too. So glucose plus 2, remember there's 2 NAD plus that's reduced, and then 2 ADP plus P forms 2 NADH, and you have 2 net gain of ATP right here. At the same time, you have pyruvate. Good. Next, link reaction. So HL, for SL, the only thing they need to know for link reaction is it either becomes lactic acid, alcohol, or carbon dioxide. For us, we need to look at steps. All right. So for the link reaction, the process is called oxidative decarboxylation. Why do you think it's called oxidative decarboxylation? Why decarboxylation?
In the matrix, enzyme removes H and CO2.
What is removed?
H and CO2. Hydrogen and carbon dioxide.
Carbon is removed. Remember,
Hydrogen.
decarboxylation means removing of carbon. So why do you think it's called oxidative? Something is oxidized. Something is oxidized. Something is decarboxylated. So please look at the picture again. So we have pyruvate. That's the end product of glycolysis. In the presence of an enzyme, we call it coenzyme A. The presence of enzyme. This enzyme. Look at what's happening. Okay. The enzyme catalyzes the decarboxylation. removes the carbon, right? There. So carbon is removed. There's oxygen in your cell, so it forms carbon dioxide. All right. Now, why is this called oxidative decarboxylation? What is oxidized here? Which molecule is oxidized here?
CO2.
Harvard.
Pyruvate.
Oh.
Pyruvate is oxidized. So oxidation is loss of electron and hydrogen. Where did the electron and hydrogen go? We have an electron carrier again, right? So NAD plus is reduced. Pyruvate is oxidized. In the process of a coenzyme, it's also decarboxylated. So pyruvate is oxidized and decarboxylated. It lost electrons, it lost hydrogen, it lost carbon. So what are the products? NADH plus H plus, acetyl coenzyme A, and carbon dioxide. Repeat. Pyruvate is oxidized. It's also decarboxylated, correct? So this is oxidized and decarboxylated. So what are the products when it's oxidized and decarboxylated? Product is reduced NAD plus or NADH plus H plus, acetyl coenzyme A, and carbon dioxide. You want to put that in a sentence. Because pyruvate is oxidized and decarboxylated, it forms NADH plus H plus, acetyl coenzyme A, and carbon dioxide. Children, this is called a link reaction. Where does this happen? Matrix. Remember where the matrix is? Okay. So pyruvate was initially in the cytoplasm. It will enter the mitochondria, go inside the matrix. This is why the matrix up because that's where the enzymes are present. So once it's in the matrix, pyruvate is oxidized and finish my sentence, please. Pyruvate is oxidized and decarboxylated. And it produces
Oxide.
this is called the link reaction. Okay? Link. Because it's going to link what's happening in the cytoplasm to what will happen in the mitochondria. All right. So, where will the NADH and H plus, where is it going to go? By the way, did we produce this in glycolysis? Yes. We also produce how many? 2. So in glycolysis, we produce this. In link, we also produce this. They will all be used in ETC. That's not a channel in your cable. Although I like ETC channel. It will go to Electron Transport shape. Later on. Where will this go? This will proceed to the next step called the Krebs cycle. Where will this go? It's a waste product. This is what goes into your blood and then eventually you breathe it out. Okay, so the product again, NADH plus H plus, acetyl coenzyme A, and carbon dioxide. It says here 2 acetyl coenzyme A because how many pyruvates per glucose molecule? 2 pyruvates, right? So each pyruvate can form acetyl coenzyme A. Their total amount of acetyl coenzyme A is 2 acetyl coenzyme A. Okay. Summarize again. First bullet point. Pyruvate from glycolysis, matrix. Summarize it. Pyruvate from glycolysis, matrix. Put arrows. Like summarize it, please. But just go back to your notes later on. Second, remove carbon dioxide and hydrogen. Actually, this is remove carbon dioxide, hydrogen, and electrons from pyruvate. Next, NAD to NADH. Next bullet point. Maybe. That's nice to know. Removal of hydrogen, oxidation, removal of carbon dioxide, decarboxylation. Therefore, we call it oxidative decarboxylation. I like my definition. My earlier definition is oxidative decarboxylation because pyruvate is oxidized. Pyruvate loses hydrogen and electrons. Pyruvate, you loses carbon dioxide. That's why it's called oxidative decarboxylation. What are our products? Acetyl group, which proceed to the Krebs cycle. Carbon dioxide also is a product, and NADH is our product. Where did this come from? The link reaction. This was our product in the link reaction. So if this one is not the matrix, right? It will bind with a 4-carbon molecule. You don't need to know, but it's oxaloacetate. Just know it will bind to a 4-carbon molecule. So 4 plus 2 is 6. So it will form a 6-carbon molecule called citrate. You don't need to know again. Just know 4 plus 2 becomes 6. Now, what step is this? Okay, we've learned the different chemical reactions, right? Remember decarboxylation. So we're removing carbon again. So 6 becomes 5. Miss, why is it oxidative decarboxylation? What will this lose?
Carbon dioxide. Carbon.
Oxidative. Oxidation, what will this lose? And hydrogen. So this will undergo oxidation, electron, and it will lose oxygen. It will lose electron and hydrogen. Where will that electron and hydrogen go? To your NAD plus again. So NAD plus is reduced. This citrate is oxidized. This citrate is also decarboxylized. So the citrate is oxidized and decarboxylized. So it loses hydrogen, electron, and carbon. Clear? To become a 5-carbon molecule. Now, this 5-carbon molecule again is oxidized and decarboxylized. So if it's oxidized, it will loses what again? Hydrogen and electrons. Where will that go to? NAD plus. Because it's decarboxylized, it means 5 carbon will become 4 carbons. Okay, let's keep going. So this 4 carbon will have a rearrangement of its elements. The rearrangement of the elements produces ATP. Remember substrate level phosphorylation? It means direct addition of phosphate. Where will the phosphate come from? Probably from here. Okay. I didn't draw the whole molecule. I just drew the carbon. But if this is phosphorylated, ADP is phosphorylated into ATP. Where will the phosphate come from? From your 4-carbon molecule right here. But miss, this doesn't have phosphate. I know, but how about this one? This will have phosphate. Anyway, okay. So phosphate comes from this 4-carbon molecule. Phosphate is directly added to ADP to form ATP. That's why it's called substrate level phosphorylation. And look at what's happening here. Oxidation and reduction. Your NAD plus is reduced. Your FAD is also reduced. So this 4 carbon is oxidized. 4 carbon is oxidized. And this 4 carbon has phosphate removed. So what are the products? ATP, NADH plus H plus, and FADH2. The final product will be that oxaloacetate ready to bind with another acetyl coenzyme A. So for one glycolysis molecule, you have how many pyruvates? 2. So this needs to happen how many times? Twice. 1 cycle per pyruvate molecule. Summary. Acetyl coenzyme A, Krebs cycle. Maybe copy this later. Let's just understand this now. So 2 carbon acetyl plus an existing 4 carbon will form a 6 carbon molecule, which will undergo oxidative decarboxylation to produce what? 5 carbon compound, CO2, also NADH plus H plus. And then, along with the 3 NADH plus H plus and 1 FADH2, per molecule of pyruvate. So these are the products per molecule of pyruvate. You also produce ATP, and this NADH and FADH2 will proceed to the next step, which is the electron transport chain. Almost done. Last is
Yay.
this two I said is together. We call this, what did I say earlier? Oxidative
Phosphorylation.
Wow.
I can't say the word.
Oxidative. All right. Let's look at what's happening here. This is the inner membrane space. The inner membrane. Inner membrane, and then intermembrane space. What is this here then? Matrix. All right. So in the matrix we have NADH plus H plus, right? This NADH will lose electrons. Please look, electron will go here in the first protein carrier. And then it will jump here, to here, to here. As the electrons jump from this to this protein pump, hydrogen is pumped out into the, what is this place here? Intermembrane space. Remember, you have plenty of this, NADH and FADH2. So all of those molecules will lose electrons. Remember I told you they picked up electron from glycolysis, from Krebs cycle, and then here in the electron transport chain they lose it. They lose it here in your electron carriers. These are protein pumps. So they lose electrons. Electrons will jump from protein to protein. As electron moves from protein to protein, it energizes the protein to pump protons out. Okay? So this is what's happening to FADH2. Again, it loses electrons. Electrons jump from protein to protein. It energizes the protein to pump protons out. As that keeps happening, what's happening? You have accumulation of protons here. So check for understanding, where did this come from? NADH plus H plus N, FADH2. How is it pumped here? Movement of electrons. Movement of electrons from here to here to here energizes the proteins. These are proteins. These are not arrows in your cell. They're proteins. So they're energized and they can pump protons out here. All right, very good. So what will happen now once protons accumulate? You establish a gradient. So there's a gradient. There's a concentration difference. There's much more protons in the intermembrane space than the matrix. Because there is a gradient, where will the protons move? From the intermembrane space back to the matrix. What's so special with this? Well, as they move back into the matrix, they pass through an enzyme called ATP synthase. What's the name of the enzyme? ATP synthase. So they pass through the ATP synthase back into the matrix. So what missed if it passes through ATP synthase? These are all protons. They're all positively charged. They can energize this enzyme. Now, let me use an analogy. For example, you have a tub. You know what make paper boats? Full of paper, and then you have paper boats. So you put paper boat here, paper boat here. And then try to spin the water with your head. Spin it faster. What happens to the paper boats? Closer, right? I spin it. Closer. So scientists use that analogy. If this is energized, it spins. So once it spins, you have ADP and P. ADP, P.
ATP.
Spin. What do you form? ATP. So that's how ATP is formed. If we want to rewind, how is ATP formed? You have an energized ATP synthase. How is this energized? There was a proton gradient. Where did these protons come from? It was pumped by these proteins. How does these proteins pump it? because electrons pass through them. Where did the electrons come from? NADH plus H plus and FADH2. Where did NADH and FADH2 come from? Krebs cycle. How is it generated in the Krebs cycle? Because there was acetyl coenzyme A. Where did that come from? Link reaction. Where did that come from? Pyruvate. Where did that come from? Glycolysis. Okay, so let me clarify two processes here. I hope you understand at this point. Why do you call this electron transport chain? What is a chain?
Connected.
Connected, right? Series, something connected. What is my chain here? This protein. So those are protein chains. Why do you call it electron transport? Because
It
electrons move, actually jump. Jump from one protein to the next protein to the next protein in the chain. So it's called electron transport chain. What does it do to the protein? It energizes the protein so that the protein can move protons from the matrix into the intermembrane space. You need the electron movement in this chain so that the proteins can move protons out into the intermembrane space. It's okay, just for clarity. So we're clear. Do you understand why it's called electron transport chain? Okay. Next, another word you need to know is chemiosmosis. Why do you think this is called chemiosmosis? Osmosis of what?
Chemical substances.
Chemical. What is moving here?
Hydrogen.
The protons. The protons. That's why it's called chemiosmosis. There's movement of these protons. Okay? There's movement of protons through, what's the enzyme name? ATP synthase. Okay. Now, hold on. Okay. Now, my next question is, why do you think, two more things and then I'm done. First, why do you think this is called oxidative phosphorylation? Remember, together, electron transport chain, chemiosmosis, I said together, it's called oxidative phosphorylation. What is oxidized here?
The NADH.
Very good. This time, NADH and FADH2 is oxidized, meaning they lose electrons. They also lose protons. Okay. Why is it called phosphorylation? Formation of ATP. ATP plus P is phosphorylation. Now, how is this different from substrate level phosphorylation? I said earlier, substrate level is direct binding of phosphate. This one, did we directly bind it? Oxidation needs to happen first. That's why it's called oxidative phosphorylation. Oxidation needs to happen first so that you can form, what do you form here? ATP. That's why it's called oxidative phosphorylation. And oxidative phosphorylation is made up of two things. What are the two things? Electron transport and chemiosmosis. So electron transport and chemiosmosis are coupled, meaning they need to work together. If you write it in a sentence, electron transport chain is coupled with chemiosmosis for oxidative phosphorylation. Or in English, ETC plus chemiosmosis equals oxidative phosphorylation. Now, second thing, and then I'm done. Bathroom again. Now, oxygen, how is this aerobic respiration? Remember, whatever I'm explaining is aerobic respiration. Why do we say this is aerobic respiration? What does it mean when you say aerobic? It happens in the presence of oxygen. Did I even mention oxygen anywhere from the beginning to now? Nowhere, right? No, just hydrogen, just the electron. So this is where I'm going to mention oxygen. Oxygen, which is present inside your cell, will be your final electron acceptor. Here's what do you mean? Electron jump, 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 right? Jump, jump, jump. Where will they eventually go? Back, jump, jump, jump? No. Those electrons jump, jump, jump. The final electrons will be accepted by oxygen. And remember, you have proton, increased protons here. It will move in. That proton, together with electron, form this. Will bind with oxygen to form water. So oxygen plus electron plus proton forms water. So this is aerobic respiration. What will happen if there's no oxygen? Proton moves, right? At some point, it's just going to be equal. There's nothing to establish the gradient. So every time proton moves in, it goes to the oxygen. So you still have a gradient. So proton keeps moving in, it keeps going to the oxygen. Right? So because there's oxygen, there's something that removes the protons that moves in. So that you can have a gradient. So it will keep moving into the matrix. Another thing, well, electrons jump, jump, jump. Where will it go? I mean, it needs to go somewhere. So that electrons will eventually bind with oxygen. So again, oxygen plus electrons plus protons will form water. So we say oxygen is the terminal. I think the book used the word final. It's the final electron acceptor. Can I also say it's the final proton acceptor?
Yes.
Yes, it's drinking water. So oxygen accepted protons and electrons to form water. First, electron transport chain is found in the inner mitochondrial membrane. Yeah? Second, hydrogen is transferred from hydrogen is transferred by hydrogen carriers. There's two. And then hydrogen carriers release these electrons, which are transferred or jumps between different carriers, right? Ding! This releases energy. This energy is used to pump protons from the matrix to the intermembrane space. Ding! Protons will accumulate in the intermembrane space, therefore resulting into a concentration gradient.
Oh.
And then once you have a gradient, the ions go back to the matrix. Through where? ATP synthase. Okay.
Too much
Ding, 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 ding. This produces ATP by chemiosmosis. Really? Chemiosmosis. And oxygen needs to be the final. If this was a play, oxygen is the final character to come out of the stage. And by the way, I'm oxygen. I need to receive electrons and protons. I can form water. All right, let's end with, remember how I started with the structure of the mitochondria? I'll end with the structure of the mitochondria again. Because there's a reason why the mitochondria needs to look like this. Let's start with the inner membrane space. Inner membrane. Inner membrane, this, right? The fold is called a cristae. Why do you think it needs to be folded? For more diffusion. Surface area for what? What's found here? The protein pumps, the electron transport chain, correct? The more folds, the more surface area for your proteins involved in the electron transport chain. Very good. Next, matrix. What's important in the matrix? What do you think is present in the matrix? Enzymes used in what happens in the matrix? Krebs cycle and the link. So this will contain enzymes for the link and the Krebs cycle. Do you think the intermembrane space has an importance? Without reading, I don't think. Okay, don't read. What is the importance of the intermembrane space? The intermembrane space needs to be smaller, gradient. Small. Why? Gradient. The smaller it is, the faster you can establish that gradient. If it's big, it takes a while for all those protons to accumulate and form a gradient. So in intermembrane space, it says there's a small space so that the protons bumped into the space can quickly generate a gradient. Why do we need a gradient?
So we could,
For chemiosmosis, so that you can generate ATP.